In previous class, actually, we have told you how to deal with if you have parallel reactions, reaction 1 and reaction 2. And first of all, don't forget how to know your interesting reactions involved parallel reactions. First of all, you need to measure the consumption rate of reactants at different temperature. Then plot log R versus 1 over T. As long as you got the curved line, and after fitting, you got 2 straight lines. That means that there are 2 chemical equations involved in your interesting reactions during this temperature. And at high temperature, is reaction 1 dominate with and also at low temperature is reaction 2 dominate. And based on the characteristic, always is the faster one reaction with the faster reaction rate 1 dominate the whole dominate my interesting reactions. That implies that the relationship between reaction 1 and reaction 2 belongs to parallel reactions. So based on previous class, as long as you know you have a reaction 1 and reaction 2, and also they belongs to parallel reaction, then you can, based on the series design of your experiment, you can get the K1 and K2 for reaction 1 and reaction 2 respectively. And here we are going to tell you if after measuring the consumption rate at different temperature, then I also got a curved line, but it turns out that after fitting, it always the slowest reaction with a slow path dominate the whole reactions. So slow path dominate, that tell you that the relationship between the reaction 1 and reaction 2 belongs to a series reaction, right? So to deal with this kind of series reaction, how to get the K1 and K2 in your experiments? So here, I'm going to give you an example. It's irreversible reactions in series. So here, what we have is we have a reactant A will generate R with rate constant K1, and also R can generate S with rate constant K2. So apparently, this is irreversible reactions, and also is a series reaction. So following, we are going to try to write down the consumption rate minus RA and RR and also RS, the production rate of product S. So first of all, you need to write down the consumption rate of reactant A can be expressed like minus dCA over dt. Right? And we assume it is a first order reaction, so it will be K1CA. And what's the RR? A generation rate of R is dCr over dt, right? The change rate, the concentration change rate of R, you need to consider this reaction is going to, this rate equation with K1 is increased R, and this will be decreased R, so it will be K1CA and minus K2CR, so you got the RR. And how to formulate the RS, the production rate of S? dCs over dt and K2CR. So now you successfully have RA, RR, and RS. So next, based on the first equation associated with CA, and combined with the initial conditions is before reaction happens, we know the concentration of reactant A equals to Ca0 and also Cr equals to Cs equals to 0. Based on these initial conditions, then we can get move Ca to a left-handed side, dt to a right-handed side, and take the integral on both sides. Ca is integral from Ca0 to Ca, and t is from 0 to t. Then you got these solutions, and Ca as a function of t. And so we can write down Ca can express like as a function of t. Then you can observe here, at t equals to 0, then before the reaction happens, and the initial concentration of reactant A equals to Ca0. Then after that, it obeys exponential decay as a function of t, right? Okay. And yes, now you already know the Ca, right? So we know this one. And this is the differential equation of Cr. So we can just move this term to the left-handed side, becomes to here. And this one, we just try to substitute Ca with this Ca0 exponential minus k1t. We got this results. So based on the engineer mathematics books, you know the solution for this differential equation can be you can obey this standard there's a corresponding solution for this standard differential equation, right? And here y is a Cr, so you find that p equals to k2, y also Cr, and q belongs to this one is a constant, right? So based on the corresponding solution for this particular differential equation, and combined with also the initial condition before the reaction happens, we know Cr0 equals to 0. So we can have Cr concentration of R as a function of t expressed like this. And now we know the Ca, Cr, and also you know Ca0 is the beginning concentration of reactant A. Ca0 can be expressed like equals to Ca plus Cr plus Cs. Because we know this one, and this one, so we can get the Cs expressed like this as a function of t and k1, k2. K1 is a t, right? You know as a function of t. So yes, doing your experiments, you also can measure the concentration as a function of time to get the curves. For example, like this blue curve is Ca. So before the reaction happens, we know Ca equals to Ca0, then it will obey the exponential decay minus exponential minus k1t. And R, yes, you got this R, right? Cr, right? But when you try to measure the concentration of Cr, you got these curves in red. You can expect that A will increase the concentration of R, but some R will convert it to S. So definitely there's a maximum concentration of R, and will be expressed like this. And regarding to Cs, always is increase, right? And it should obey the exponential. It's like this. So next, we are going to try to convince you what the results you learned from previous slide is what in series reaction always slow path dominate. This description, we want to confirm this description or these results based on based on this deviation. So we assume K2 is much larger than K1. What's K2 much larger than K1? This is fast. This is very slow. So that means A generate R is very slow. But as long as you have R, then you will immediately generate S. So you only have small chance to observe R in this series reaction because K2 much larger than K1. So based on this, we want to try to formulate a CS because it's a generation rate of product S. So if K2 is much larger, this is much larger, say you can drop this term out, and this is much larger than this, you can drop this term out. So what we have here is 1 minus exponential minus K1t, expressed like this. So when K2 is much larger than K1, then the concentration of product S is dominated by what? K1 with a slow path. K1 means the slow path, right? So slow path dominate the production rate of S in this series reaction. And on the other hand, is if K1 is much faster than K2, this is very fast that A generate a lot amount of R, but some of R can generate S. So under this situation, K1 is quite large, right? So you can drop this term out. And this is larger, much larger than this one, drop this term out. So what we have is 1 minus this exponential minus K2t. K2 is the slow path, slow reaction, right? Because this is small. So yes, the generation rate of product S is dominated by K2 with, and this one is a slow path. It's a chemical reaction with a small rate constant, K2, okay? So next, yes, you already confirmed what you learned in the series reaction, always the slow path dominate. Then next, how to get the K1 and K2. So here, as we know there's definitely a peak concentration of CR. So you know the CR, so you can take the first deviation on dt. So dCr over dt equals to 0. So you will get the Tmax. And also, you got the CR max. So also you have two unknown parameter K1 and K2. You also have two equations. So you have chance to solve what's the K1 and K2. But some people probably will have questions that if it's very difficult to measure the CR, are there any chance to estimate K1 and K2? Probably you can use the, I would suggest otherwise, if you make sure K2 much larger than K1 or K1 much larger than K2, then you have chance to, just based on the Ca and Cs as a function of T, then you have chance to estimate the roughly value for K1 and K2. For Ca curve, you can know the K1, right? And if it is either cases, then you have chance. Only this one you have chance to know the K2. But in realistic, to get the correct K1 and K2, I will suggest you to measure the CR as a function of T, and based on this maxima, T maxima and CR maxima, then you can get the exactly value for K1 and K2. Okay, so this slide actually is a summary for previous slide and show you how to get the K1 and K2 for the series reaction, and which belongs to irreversible reactions. And next, before we ended the chapter 6, we are going to give you an example related to the first order reversible reactions. Before this slide, actually all the reactions we show you or demonstrate belongs to irreversible reactions by using the integral method, right? So this is the only case we are going to show you how to use the integral method to get the solution or specific solutions for first order reversible reactions. So now we have the product A can convert to reactant A can convert to product R with rate constant K1. And because it is reversible reaction, chemical reactions, so we also have the R can convert it to A with rate constant K2. And we assume when this reversible chemical reaction reaches equilibrium conditions, then at that moment we have a rate constant Kc. And initially, before the reaction happens, we have the Cr0 over Ca0 equals to m. That means the ratio of the concentration of R versus the concentration of A in the beginning before the reaction equals to m. So based on this and additional, we know XAE. XA is the fractional conversion of reactant A at equilibrium conditions, so equals to 1 minus CAE over CA0. And we put the E at the bottom, means that under that is under the equilibrium conditions. So we can easily write down the generation rate dCr over dt generation, so it's a plus, it's a positive, and we consume reactant A will be a minus dCa over dt. You can express, you can substitute the minus dCa becomes to Ca0 dXa based on based on the slide we introduced you in the beginning of the integral method. So here, Ca equals to initial Ca0 minus reacted portion. So you take the first deviate, so you got a minus dCa equals Ca0 dXa. So we can substitute minus dCa becomes to Ca0 dXa. This can become what? Because dCr dt, so it would be K1 Ca is going to increase the Cr, right? And also minus K2 Cr is going to decrease the Cr. So here we want to substitute the Ca and Cr. So what Ca can be equals to Ca0 minus reacted portion Ca0 times Xa, right? This is reacted portion, and minus K2, and how to express the Cr can become a Cr0, initial concentration of R. Cr0 becomes m times Ca0, and plus what? The reacted portion to become converted to R, so you plus the same amount of converted reacted portion, so plus Ca0 Xa. Is a converted A becomes to R. So now you have this differential equation of Xa, right? But inside here we still don't know two important parameters, K1 and K2. So how to get this one? By using the equilibrium conditions. So we assume at the equilibrium conditions, what's the equilibrium means? That means how much A converted to R will be equals to how much R converted to A. So that means the dCa over dt does not change over time, right? So concentration of Ca does not change with time. So at Cae means at the equilibrium condition equals to 0. So that also tell you K1 Cae equals to K2 Cre, because how much A converted to R will be equals to how much R converted to A at equilibrium condition. So based on these two important information here, then we can get the relationship between K1 and K2. So how to do that? As we mentioned, rate constant at equilibrium constant, we can express like a K1 over K2, right? Kc equals to K1 over K2. And K1 over K2, so you got the Cre over Cae, right? And here, how to get this? We use this conditions. is dCA over dt equals to 0 at equivalent condition. So dXA over dt should be equals to 0. So this equation, this portion equals to 0. So you got the K1 over K2 becomes to this over this. You just move this term to right-handed side and divided K2 to the left-handed side and this one to the right-handed bottom side. Then you will get this. Okay, so based on this, you know the relationship between K1 and K2 and use the K1 to substitute this K2. So you will get these results as long as you use this to substitute K2. And also we move the XA related part to the left-handed side dt to the right-handed side and take the integral on both sides. Then you will get these results. And if you take this as y-axis, t as the x-axis, and you input the xa at different time points, and if this curves you got is a straight line, then the slope will belongs to this. If you got a straight line, that means the equation we talk about or you are interested in is belongs to first order reversible reaction. And from the slope of this straight line, then you can get this value. And as you know, we know the m, right? Because m is a ratio, initial ratio of concentration ratio of CR0 and CA0, so you can get XAE based on this analyze. And this is the solutions for first order reversible reaction. Some people will ask, first order, how about can this solution, particular solution form, can be used for irreversible reaction, which we derived in previous slide by using the integral method. So what's the irreversible reaction? Irreversible reaction means what? The A will totally converted to R. So what's XAE for the irreversible reactions? Total XA, or total A will be converted to R, so XAE will becomes to 1. So under this situation, this you can drop this, right, m plus 1, this becomes to 1. So this, and also this will be becomes to 1. So what you get will be this one. This result actually is the same with what you derive from previous slide for the first order irreversible reactions. So we can use this solutions, particular solution, to deal with this solution for reversible reaction to deal with the irreversible ones, because for irreversible one, the XAE becomes to 1. And the rest of parts are the same, right? Okay, so I'm going to give you a summary here. So for the differential method, we introduce to you, I will suggest to you to use the half or fractional lifetime analyze to get the reaction order for your interesting chemical reactions. And how to do that? You just need to know the half-life time at different initial concentrations. Then you can plot the log T versus log CA0. Then the slope will become 1 minus n, so you can get the n. So the n, this analyze method can deal with whether, no matter the reaction order is integer or not. And the rest of parts, we spend lots of time to introduce you the integral method. For integral method, you only, because we spend some slides to introduce you the particular solution form for zero order, first order, and second order. So you need to input the CA at different time points. Then you can check whether your interesting reactions belongs to 0, first or second, by what checking the slope, whether the slope is a straight line or not. If it is a straight line, then it belongs to that order rate equation. And the integral, the more important part for by using the integral method will be to deal, you can get determine the K1, K2 for for the parallel serial reactions. And also, you can deal with the reversible reactions. The example we show you is a first order reversible reactions. And also, irreversible rate equation can be reduced from the reversible rate equation by assume the XAE equals to 1. Okay? Okay, so we ended. So we finished the lecture 6.